I am going to talk to you about a project that a team has worked on for the past year, SkyRL, a modular RL library for LLMs. Obviously, I'm here to represent a big team behind me, as you can see from the list of contributors. They're not just from UC Berkeley, but also close collaborators from Anyscale, Datadog, Stanford, the Terminal Bench community, etc. So without further ado, let me get into it. So here is the agenda I have for today's talk. Uh, First, I will go over the background of the SkyRL project, how the project has evolved over the past year. And because I think maybe many of you have heard about the project, but is still kind of confused what it specifically entails, I'll go over that. Specifically, starting from the first release, the V0, which spawned 3 more projects under SkyRL, the SkyRL, the training backend, SkyRL agent, SkyRL-TX. And then I'll give you an overview of I'll focus on the first component, the SkyRL, throughout the talk. I'll give you an overview, the design principles, systems diagram, etc. And then I'll go over some of the recent updates and next steps that the team are working on or thinking about, such as Tinker-ification of the framework, fully asynchronous RL, single or multi-turn, agent integration, where I'll use Harbor as a specific example, and also various other things like LoRa, stepwise training, vision language models, and many more. And after the SkyRL part, I will quickly go over the SkyRL agent project and the SkyRL-TX project, because I didn't quite work on the last 2 projects, so I don't have expertise. I'll just quickly go over them and then give you some quick pointers in case you're interested. Okay, so first, the background. Okay, before diving into SkyRL's background, I'll give you some generic background. So the RL community has witnessed various paradigm shifts. About around like 2 years ago, it was reinforcement learning from human feedback. And the workload characteristics are it's single turn, it's mainly text generation, there's no tool call, it's usually short input and short output, and people usually co-locate and tightly couple the 2 components, training and inference on the same set of hardware. And about maybe towards the end of 2024, people started working on reasoning RL. And now the workload becomes longer context and also longer generation. And therefore, the inference starts to dominate the training step time. And roughly April or March last year, people started looking into the multi-turn agentic RL, which uses a lot of tool and interacts with the environment. So now the characteristics become multi-turn, while besides generating text, but also there's execution of the tools and being both long context and long rollouts. And we not only have inference as a systems component, there's also the environment. So yeah, systems requirements evolved and diverged for each component, and we must rethink the RL stack design. So with that background in mind, we developed SkyRL V0. I shouldn't really say we, because at that time I wasn't admitted as a PhD student yet, but the SkyRL team worked on this during February to May of last year. This was the first release training real-world long horizon agents via reinforcement learning. Specifically, the team looked at real-world long-horizon agents, such as software engineering agents, where the number of steps may exceed like 50 or more to, say, resolve a GitHub issue. And there were various systems optimizations, which I will get into later. But specifically during that time, most of the RL framework they use the synchronous inference engine, and that was a big issue for the team to work on such multi-turn long horizon agents RL. And the team, on top of Virl, the team worked on asynchronous. Made the training framework use asynchronous inference, and then on top of that, there's also the 3-stage producer consumer pipeline, which I will discuss later. But overall, it brought a 4 to 5 times speed up over the baseline implementation. And besides software engineering, on Sway Bench, there was also other verticals like text to SQL, beating O4 Mini. And it was the first open source, fully open source end-to-end RL on long horizon software engineering task. So while working on SkyRL v0, there were several challenges that we met. The first one is, like I said, most of the framework used synchronous rollouts. In Virl, the VLM, it was hard to use VLM's async LLM engine. And SGLang, I think there were some open source effort on getting the SGLang async rollout support in Virl at some point last year. But besides that, there's also the complicated agent loop implementation, and was also issue with scaling up the environment. So with these challenges, we started prototyping a simpler RL framework from scratch. Yeah. And that brings to the SkyRL project. In around June 2025, we rewrote the framework from scratch. So there's no use of Virl or OpenRHF in the framework. It was from scratch. And yeah, this was the title of the blog post. It also, I think, coincides with the release of Slime, which also emphasizes modularity. So it just kind of demonstrates the importance of modularity in modern day RL workloads. So here is a quick systems diagram, which I will talk about more later. There's the controller, there's a trainer, and there's a generator. As you can see, modularized. Yeah. And while some of us were working on SkyRL, there's another group of us working on SkyRL Agent, which is released November 2025. It is an agent framework, an agentic layer on top of the RL training backends. I will also go over it quickly, but it's basically an agent layer. It allows you to define your own agent in the framework, and there are various training recipes that come along with it, such as software engineering, deep research, biomedical agent, etc. And finally, the third sub-project, I guess, is SkyRL-TX. This was released right after the release of the Tinker product. And it is an open source project to implement the Tinker API, which was October last year, which I will also go over quickly. I'll go over later. Okay, so with the background being said, now let's dive into the SkyRL framework. So just to revisit the previous slides on the RL workload background, we have three systems components: training, inference, and environment. Each of them have their own systems requirements. So given that, what do we need from an RL framework? We want, for each of the three components, we want diverse backends. For training, for flexibility, you might want to use FSDP. For a more optimized performance for models like MOE, you might want to use Megatron. For inference, maybe VLM or SGLang, or even your company's own inference engine. And for environment, there's even more diversity there. And for each of them, we want to utilize the best hardware. So what does this suggest? We need to decouple them. And in order to decouple them, we need well-defined public APIs between the components. And to orchestrate these components, we need a single controller. So yeah, what is SkyRL with those design principles in mind? This is the systems diagram. We have a controller on top, a trainer, and a generator. Within the generator, there's the inference engine, and there's also the environment that interacts with the inference engine. So first of all, controller. This is pretty simple. We use Ray to orchestrate the various resources and actors or workers. User can define their algorithm in a single controller style. And yeah. And there's also trainer. The goal is to update the parameters. We support both FSDP and Megatron. You can either co-locate training and inference on the same set of hardware or decouple them into separate hardware. And we also support LoRa, MOE. You can run ARA on a single GPU or multiple nodes, and 5D parallelism, etc. And so what does it use to train? It uses the trajectories and rewards generated by the generator. And after it trains, it gives the updated policy models to the inference engines and start the next step. So now the generator, which is I guess the more heavyweight part. First of all, we have an inference engine. The inference engine is responsible for generating the text. And from the text, we might parse out the tool calls. And with the tool calls, we will update the environment state. What? Yeah, so with the generated rollouts, we might parse out tools and like what? So yeah, so there's an environment which includes the agent loop, essentially everything besides a VLM engine that you need to generate those trajectories and rewards. We have an in-house agent loop called SkyRL Gym, which uses the Gymnasium API, which is very simple and lightweight. We support like math, code, search, or SQL, and other tasks. But you can also bring your own agent. Yep. Okay, so that is the systems diagram, and zooming out, the modularity of it really allows you to substitute any part with the thing that you want based on your requirements. So that was the overview of SkyRL framework. Now I will go over some of the recent updates and the next steps that we're thinking about. The first one is Tinker-ification. What I mean by Tinker-ification is to make SkyRL Tinker API compatible. So what is Tinker? Thinking Machine Lab released Tinker last year around October. It is a training API for researchers. It exposes 4 core APIs, 4 backward, which accumulates the gradient using the inputs, and it optimizer step, which updates the weights of the model based on the accumulated gradient, and also sample. With the updated weights, you can just do inference. And finally, save state, which saves the training progress for resumption among other states. And right after the Tinker product was released, our team decided that there's a clear need of an open source implementation of it. This effort is led by Philip Moritz, the CTO of AnySkill, who is still actively working on it. He even has more commits than I do, a PhD student, which is pretty cool. And also Tyler Griggs from Skylab. And this is the first open source Tinker backend. And some of the features include it unifies training and sampling. Like you can run training and inference with the same model definition, meaning that the precision is unified. And it's also written in JAX, which means that it not only runs on GPU, but also potentially on TPU. So, yes, okay. So what is nice about this Tinker API? So we believe that this API is at the right level, at the right abstraction level. It is small, simple, very well defined, such that the users can not worry about infrastructure at all, but just focus on the algorithms and recipes. And it's also flexible. By composing these 3 APIs for backward, optimizer step, and sample, you can essentially express a lot of algorithms, either not only RL, maybe also SFT and many more. And it's also an opportunity for an open standard, such that we can unlock a network effect in open source to easily share training code. What we mean by this is, for instance, imagine a research team use the Tinker product to do their research, and now I have my own GPUs and I want to reproduce that. It's not a trivial task to do it, but if the RL frameworks are compatible with the Tinker API, you can use the same script that was used to run with a Tinker product with your own GPU on, like, say, any other cloud provider. So with that motivation being said, SkyRL's Tinkerification includes exposing the Tinker API surface. And instead of running on Thinking Machine Lab's hosted infrastructure, it's going to run on SkyRL managed workers. And we need to give users the right ergonomics to use those APIs. So here is a quick systems diagram. On top is the environment, which is kind of separate from this Tinkerification. And here is the core entry point, the user's training loop. It can be the Tinker cookbook, which is the, I guess, a cookbook that was released with the Tinker product. And with that entry point, it's going to call those REST API servers APIs, like forward, backward, optimizer step, sample, save state. And those API requests are going to be dispatched into an engine, and that engine will batch the forward backward passes, schedule optimizer step, or trigger weight sync or sampling. And those requests are in turn executed by the worker implementation, which again is the same trainer and inference engine that we saw on the earlier slides. And on the right-hand side, there's the database that stores the job queue and the metadata, and also the storage that stores the model checkpoints. So yeah, that was Tinker-ification. Feel free to reach out to us after the talk. We are really excited about this direction. And the second update that I want to talk about is fully asynchronous RL, single turn or multi-turn. So this is two figures from the RL paper, which was released sometime last year. So this is to kind of motivate what fully asynchronous RL actually is and why we need it. So here is a typical paradigm called synchronous RL, where the blue is generation, orange is training, yellow is loading weight. So one thing to note is that both the training and generation, they are co-located on the same set of GPUs. After generating the rollouts, we train and then we update the weight, and then we offload the training and then load back the VLM or SGLN engines and generate again. So there's that. And there's also another paradigm called one step off async RL, where we can now separate the training and inference on separate GPUs, where the goal can be you want to scale them separately because they have different systems workload characteristics. But here, for instance, I generate the first batch. While training on that first batch, I generate the second batch, so now it's overlapped. This is good, but as you can see, there can be stragglers in the generation. For instance, if this request takes a really long time, the entire system is stalled, which is not what we want. So here comes fully async RL. It's also called like in-flight wait update RL or preemptible generation, etc. But the idea is that I generate, and then as soon as I finish generating a mini batch size of requests, I kick off the training worker, and right after the training is done, I pause the ongoing generation, update the weights, and then continue those requests with the new weights. In other words, the same request can be generated with multiple model versions. And so with this, there, as you can see, there's no straggler because you don't need to wait for any specific request. You just preempt them and then continue with the new weights. So yeah, so SkyRL modeled after the RL implementation and supported in SkyRL. This is a quick systems rough diagram. On the left-hand side, you have the generation workers. On the right-hand side, you had the training worker, which is kind of like the main loop, I guess. And in the middle, there's the async. These are the, I guess, control logic structures. There's an async data loader. There's a stillness manager. The stillness manager like kind of controls how off policy you can be for this async RL. And there's also the buffer. And so here, these guys are the producer to the buffer, and the training worker are the consumer to the for the buffer. And it is worth noting that this async RL implementation works out of the box for any agent. And why is that? That is because when you pause the generation, sync wait, and continue generation, the agent does not know anything about it. That is because the chat completion requests, for instance, with sync RL, the semantic of this is you just you just complete the request autoregressively. Now with async RL, the semantic is still, I complete the request, but in the middle, there could be some synchronous syncing waits or some preemption, etc. But the agent doesn't need to know any about it, doesn't need to know any of it. So yeah, so this implementation supports any agent out of the box, which is great. And here are some quick results of validating the implementation. So we ran DAPO with Qwen3 1.7 billion parameter. These are some graphs where the brown curve is the synchronous baseline. The x-axis is time, so it's wall clock time. This is the reward over time. This is the average pass at 16 over time, and that is the evaluation over time. And the brown curve is the synchronous baseline. Pink and purple are max stillness being 1, and orange, red, max stillness 2, and the green ones are max stillness 4, and blue are max stillness being 8. But the takeaway is that with more max stillness, even though it's more off policy, but the speed up you get kind of like uh, kind of give you a better convergence time over wall clock, a better convergence over wall clock time. Yeah. And this is another diagram kind of breaking down the time with the different stillness. As you can see, this is this timing of each step. With max stillness 1, it's roughly 60, and with more stillness, it's increasingly shorter. And that is because the time we spend on waiting for the generation buffer is increasingly shorter. So that's just a quick validation of the implementation of fully async RL. Okay, next item, agent integration. So again, this is the systems diagram. We support SkyRL Gym, an in-house environment, which uses the gymnasium API. You can use this for like, I guess, deep research or some like lightweight type of tasks. But you might not be satisfied with that, so you can bring your own. For instance, we integrated with Prime Intellect's verifier hub, Minisway agent or open code, and in order to bring your own custom environment or custom generator, you just convert the problem into your agent's input that you want. And then instead of, say, using the OpenAI API, OpenAI endpoint, you use our own inference engine's served endpoint. So you don't need to change your code at all. You just change the API, and then you can inference with the updated weights. And finally, when a rollout finished, you convert the chat history or reward back to what SkyRL wants, and then that's it. And one example of such agent integration I want to point out is Harbor. So Harbor is a repository co-led by the co-creator of Terminal Bench, Alex. And this is kind of a standard interface for agentic tasks. It is widely adopted for agentic evaluation. So the main, I guess, motivation of this framework is to evaluate on Terminal Bench. But since you can evaluate on Terminal Bench, you can also do SFT, generate the SFT traces with it. And you can also do RL with it because you can generate a rollout with that framework. And it also handles the sandbox spin up and scale up. And so one of the user of this integration is the OpenThoughts project, which is led by the OpenThoughts team, which is a data-centric approach of training for terminal bench style tasks. It uses SkyRL plus Harbor integration. The reason why I want to highlight this user example is because there are likely many of the users out there that want to train for terminal use style tasks, and yet they're likely not RL experts. So what should we do? We should just integrate SkyRL and Harbor such that they just need to worry about the data and the recipe, which is what they're good at, and only iterate the data and without worrying about the integration or the correctness or the infrastructure, etc. So yeah. And finally, some other various updates we have. We improved the large-scale MOE training with Megatron. We improved the LoRa support. And some of the things that are in progress are stepwise training for rollouts that need context management, multimodal support, specifically vision language model, and also keep improving that Harbor integration. For instance, support both Terminus 2 and OpenHands for the agent loop, and many more. And I don't have time to go over them, but please come chat with me after the talk or offline about any of these that you're interested in. Okay, almost done. So that was the SkyRL part. Now I want to quickly go over the SkyRL agent project. Again, I'm not an expert on this project, but feel free to check out the links I will have later. So this project is led by Da-Chen and Shi Yi, two other PhDs in the Sky Computing Lab. It is a framework for agentic RL. It is it is a layer above the RL training backends like SkyRL, and it comes with, so it is more research driven. It comes with recipes and existing implementations of verticals like sway bench, biomedical analysis, agent memory, computer use, deep research, and many more. And it also has some systems optimizations like the thing called async dispatch. I will quickly go over this example, systems optimization example, to give you a sense. So traditionally, async batch, we start all the requests at the same time. So initialize the environment, which can be like spinning up a container, generate with LLM. With the generation, you step on the environment and generate again, and then reward. So that's async batch. And as you can see, there's this straggler issue. But there's also another option of async batch, but with bounded number of concurrency. So here there are only 2 workers. For each worker, whenever the reward finishes, it starts the second rollout. And as you can see, the issue here is that when you're calculating the reward and initializing the environment, like spinning up a container, the GPU utilization is super low, which is very bad. And the team addressed this by having this async pipeline. So let's look at this example. 2 workers initialize the environment. While they're generating the rollouts, you prepare the next 2 environments by overlapping those with the generation. And when these 2 are done, you calculate the reward while just directly generate the LLM output. So this allows you to have a much higher GPU utilization. And this is the result for blue. This is the async batch. And this y-axis is GPU utilization. And as you can see, the blue one has a lot of dips on the GPU utilization. But with the async pipeline, it's almost always pretty high. And as you can see, the time that it takes for the end-to-end job is 1.55 times faster. This is with the software engineering agent training using the R2E-Gym dataset. Okay, so that was SkyRL agent, and now SkyRL-TX, a quick overview. So this is the open source implementation of a Tinker training backend. You can kind of understand it as on the same abstraction level of FSTP or Megatron, but with the features of being JAX-based, meaning that you can either do GPU or TPU or potentially in the future Trainium. And another is that training and inference share the same model definition, so inherently there's no precision mismatch. And also we support MOE and multi-LoRa, where multi-LoRa means that there can be multiple users, each having their own RL job, but each of them training a separate LoRa, which is kind of the idea of Tinker. So you can do multi-tenant training, because most of the time RL jobs are single tenant, but here with a set of resource pool, you can support multiple users training. Yeah, and some of the recent updates are TX supported FSTP and multi-node. And we did a comparison against VLM for inference, because here we said we support inference, so we need to compare against VLM. It's in the 0.2 release blog post. And there's also performance against Tinker itself for an RL job, GSMAK specifically. I'll quickly go over the results. So we ran GSMAK using Tinker Cookbook's rlloop.py, which is GSMAK demo. And here the Tinker ones, like the pink, blue, and gray, are the runs that use the paid API. In comparison, the purple, green, and another green is using TX with 8 H100, like your own GPUs. And we ran 3 times for each of them to get a sense of the variance. And as you can see, for some reason, TX converged faster than the Tinker Tinker runs, and the timing it takes are roughly the same. So just this is kind of like a validation of the implementation. And check out the release blog post that talks about this performance comparison for more. So yeah, so these are some quick links. Like I said, I only focused on the SkyRL part, but for the SkyRL agent, which is led by Shi and Dachin, you can check out the repo, the paper on archive, and the slides that they just presented like 2 days ago. So very up to date. And there's also SkyRL-TX, which is led by Philip and Tyler. Again, there's a repo and a list of blog posts on each of the release. And there's the talk at Ray Summit last year in October on YouTube. And yes, thank you for listening. This is a QR code